Okay, so we continue with the reactions. So in the previous lecture, we completed reactions of oxygen, reactions of metals with acids, and also with reactions of metals with water. So reactions of metals with acids, reactions of metals with water. These we did last time. Now we'll do the next part, that is reactions with oxygen. So metals react with oxygen to form metal oxides. Most of the metal oxides are basic in nature. Most of the metal oxides are basic in nature. Some metal oxides like ZNO, that is zinc oxide, Al2O3, that is aluminum oxide, etc., are amphoteric in nature. Amphoteric oxides are those oxides which may behave as basic oxides in some reactions. Also, they may behave as acetic oxides in some other reactions. Then, we will do some examples of reactions now, like we did here. Right? Examples. First, sodium plus oxygen. Sodium plus oxygen. Sodium oxide. This is the formula of sodium oxide, Na2O. This is sodium oxide. Then another example, potassium plus oxygen. Potassium plus oxygen. Potassium oxide. Third one, aluminium plus oxygen. Aluminium oxide. So aluminium oxide. Al2O3 is aluminium oxide. Zinc plus oxygen. zinc oxide, so these are the examples. Magnesium plus oxygen, magnesium oxide. So these are the examples of reactions with oxygen. So metals react with oxygen to form metal oxides. Now here you have to know some points that are related to a few specific metals. First, sodium and potassium react readily with oxygen, and and the reaction is vigorous and the reaction is vigorous. They catch fire as a result of this reaction. They catch fire as a result of this, that is their reaction with oxygen. So they catch fire as a result of their reaction with oxygen. Hence, they are stored under kerosene. So what happens is, if you want to prevent this oxidation, that is the reaction with sodium with oxygen, you have to store it in kerosene. You don't want the reaction to happen, because if it reacts with the oxygen present in the air, then it may even cause a fire. Like I said, it is explosive and the reaction leads to a fire. So it is stored, or I can say like this, immersed it is stored, or it is immersed in kerosene in order to prevent reaction with oxygen of air. So the oxygen present in the air may react with sodium, and therefore the fire may be a result. That means the fire can be seen. In order to prevent a fire, we don't want the reaction to happen, and so we store kerosene. We store sodium under kerosene. This is one important point I have made. Next, magnesium, magnesium, aluminum, and zinc do not readily react with oxygen. Do not readily react with oxygen. They react on heating. They react on heating. Third, Fe and Cu, Fe and Cu do not burn in air even on strong heating. But that means if you heat Fe and Cu with air, you will not be able to see the reaction immediately. But what happens is on prolonged heating they will react. Prolonged means you keep heating for a long time. So, but on prolonged heating, but on prolonged heating, they react. So on prolonged heating, they will react with oxygen. So we have to remember this. So vigorously or very readily, the metals like sodium, potassium, rubidium, they react. Then the metals like aluminium, magnesium, and zinc react on heating, and the metals like Fe and Cu react only on prolonged heating. Okay. Now, next type of reaction. So this was reaction with oxygen. Before that, we had reactions with water. So after reactions with water, we did reactions with oxygen. Next is reactions with salt solution. Reactions with salt solutions. Reactions with salt solutions. Now here we have to know that a more reactive metal, a more reactive metal a less reactive metal from its salt solution. So, what does this mean? If I have a salt solution of a metal and if I place another metal in that salt solution, then a reaction will happen provided that the metal which I have placed inside the salt solution is more reactive than the metal whose salt solution was taken. So the metal which is placed must be more reactive in order to carry out a reaction. So examples you can do. So such a reaction is an example of displacement reaction. Such a reaction is an example of displacement reaction. So if a more reactive, if a more reactive metal is placed in a salt solution of less reactive metal, in a salt solution of less reactive metal, then displacement reaction occurs. Then displacement reaction occurs. Examples. Let's say I'm putting Fe in a solution of CuSO4. The reaction will happen. What will happen? Fe will react with this to form FeSO4 and Cu will be moved out. Since Cu has been moved out, this is an example of a displacement reaction. This reaction has taken place because Fe is more reactive than Cu. So Fe is more reactive than copper, whereas iron is more reactive than copper, and therefore this reaction has taken place to form FeSO4 and C. Second example, if I take Zn plus CuSO4, or Zn plus CuNO3 twice. Again, same thing will happen. Zinc is more reactive than copper. Since zinc is more reactive than copper, a salt will be formed, that is zinc nitrate, and copper will be displaced or moved out. Since copper has been moved out, this is an example of a displacement reaction. If barium, then barium is a metal. If barium is reacted with, so barium is more reactive and therefore barium chloride will be formed and zinc will be displaced. So this is again an example of a single displacement reaction. So this is again an example of a single displacement reaction. Another example, copper plus silver nitrate. So here copper is more reactive than silver. Since copper is more reactive than silver, therefore copper has displaced silver from silver nitrate. So all these examples of single displacement reactions. Now if I write in the opposite pattern, that is, for example, if I ask you what will happen if this happens, if silver is placed in, if silver is placed in zinc sulfate. Now silver is less reactive than zinc, and that is why no reaction will happen. Similarly, if I write here, copper is less reactive than Fe, that is, copper is less reactive than iron, and here also no reaction will happen. So it depends on the reactivity of the metals. Therefore, we come across a concept that is reactivity series. Also called activity series. This will help us to determine which is more reactive and which is less reactive. So what is reactivity series? The arrangement of metals the arrangement of metals the arrangement of metals in the order of decreasing reactivities. The arrangement of metals in the order of their decreasing reactivities is called reactivity series. Also called activity series. So this arrangement, that means which is more active and which is less reactive, that way, if they ask, then we should be able to immediately tell. So you have to learn that series, and once we learn, we know. So let me show you the series now. So the series is like this. So this is the reactivity series. So as we go down, this series, the reactivity decreases. As we go down this series, the reactivity decreases. So if I ask you now, which is more reactive, aluminum or zinc? So aluminum will be more reactive. Similarly, which is more reactive, Fe or tin? And we said Fe is more reactive than tin because Sn comes below. Fe is much above. Whichever is below will be less reactive. So this is called the activity series. Now, point to be noted is that this is used as a reference, hydrogen. Hydrogen is used as a reference. Why is it used as a reference? Because it is present in water, it is present in acids. So we can compare with respect to hydrogen. So hydrogen is used as a reference. So with respect to hydrogen, we assess the reactivities. So if something is lying below hydrogen, it is less reactive than hydrogen. And if a metal is lying above hydrogen, then it is more reactive than hydrogen. No. First thing, a metal which is or which has a high or a good tendency to lose electrons. A metal which has a high or a good tendency to lose electrons is reactive. So, out of two metals, the one with a higher tendency to lose electrons is more reactive. Is more reactive. Then a metal which is above hydrogen in the reactivity series. A metal which is above hydrogen in the reactivity series can react with dilute acids and also with water. And also with water. A metal lying below hydrogen, a metal which is lying below hydrogen in the reactivity series does not or cannot react with a dilute acid or with water. So these are the important observations based on the reactivity series, the conclusions or the inferences that have been drawn after looking at the reactivity series. Okay. Now, one important question. Why does a metal usually not form? Why does a metal usually not form hydrogen gas when it is reacted with dilute HNO3, that is dilute nitric acid? Why does a metal usually not form hydrogen gas when it is reacted with dilute nitric acid? This is one very important question. Most of the metals do not form hydrogen gas. Most of the metals do not form hydrogen gas on reacting with on reacting with dilute HNO3. This is because the reason is very important. So this is because dilute HNO3 is a strong oxidizing agent. This is because dilute HNO3 is a strong oxidizing agent. And so it reacts with a metal, and so it reacts with a metal to form, it reacts with a metal to form water, salt, and an oxide of nitrogen. Since HNO3 acts as an oxidizing agent, since HNO3 acts as an oxidizing agent, so it itself gets reduced to an oxide of nitrogen. So I told you one thing when I did the first chapter, that is, in a redox reaction, oxidizing agent is that component which gets reduced. So in this reaction also, HNO3 is acting as an oxidizing agent. So HNO3 will get reduced. How does it get reduced? It gets reduced to some oxide of nitrogen. So HNO3 acts as an oxidizing agent and hence it gets reduced to an oxide of nitrogen. And also water is formed as a product. Any species which acts as an oxidizing agent always gets reduced. Any species which acts as an oxidizing agent always gets reduced. So remember this. And any species which acts as a reducing agent always gets oxidized. Right? So this is point number one important point, star mark. As we go down the reactivity series, the reactivity decreases. And this arrangement of metals this arrangement of metals in the order of their decreasing reactivities is called reactivity series or activity series. You have to learn this series. That is from potassium till platinum. Pt is platinum. So whenever you write a reaction with a acid, whenever you write a reaction of a metal with an acid, do not write metal plus nitric acid given salt plus hydrogen. That's a common mistake which people make. Don't make that mistake because a metal reacts with nitric acid to form salt, water, and and oxide of nitrogen. So these are the three components that are formed: water, salt, and an oxide of nitrogen. So don't write metal plus nitric acid giving salt plus hydrogen gas. Whenever you're asked to write a reaction of a metal with an acid, always write metal plus HCl, that is hydrochloric acid, or you can write metal plus H2SO4, that is metal plus sulfuric acid. But do not write metal plus nitric acid, because nitric acid reacts with the metal to form water, salt, and an oxide of nitrogen. It does not give hydrogen gas as a product. Still, here you should know exceptions. So in case they ask you for magnesium and manganese react with, so these are the two metals, magnesium and manganese. They react with very dilute nitric acid to form salt and hydrogen gas. So only these two metals react with nitric acid to form salt and hydrogen gas. Others do not react to give hydrogen gas. They instead produce water and an oxide of nitrogen as products besides salt. Okay. Now we will do reactions of non-metals. Reactions of non-metals. First, reactions with oxygen. A non-metal a non-metal reacts with oxygen. A non-metal reacts with oxygen to form non-metal oxide. Non-metal oxides may be acidic or neutral. Non-metal oxides may be acidic or neutral. So some non-metal oxides are acidic, most of them are acidic. Some non-metal oxides are neutral also. Examples: first, phosphorus plus oxygen. If we use excess oxygen, you get this as a product. Next, sulfur plus oxygen, sulfur dioxide. Also, sulfur may react with oxygen to give sulfur trioxide. Nitrogen plus oxygen. There could be many products. I'm writing just one. Let's say NO, nitrogen monoxide or nitric oxide. Carbon plus oxygen, carbon dioxide. Carbon plus oxygen may give carbon monoxide also, depending on whether the oxygen is used in excess or the oxygen is used in a limited amount. Okay. Note, carbon dioxide, sulfur dioxide, sulfur trioxide, phosphorus pentaoxide, dinitrogen pentaoxide, are acidic oxides. If they ask you to name some acidic oxides, then you can give these examples. Examples of acidic oxides. Second, N2O, NOCO are neutral oxides. N2O, NOCO. They are what? They are neutral oxides. Okay. So these are neutral oxides. N2O, NOCO. So to know these examples of acidic oxides and neutral oxides. So this was what? This was reactions with oxygen. Second, reactions with acids. So non-metals do not react with dilute acids. Non-metals do not react with dilute acids. Some of them react with concentrated acids. Some of them react with concentrated acids. The concentrated acids act as oxidizing agents and hence the non-metals form oxides, form non-metal oxides. Don't need to know the reaction. This much is sufficient for you. You don't need to write any chemical reaction for this. Reactions with bases. Some nonmetals react with bases. Like chlorine is a nonmetal, so chlorine is reacting with base, that is NaOH. Chlorine is reacting with the base, that is sodium hydroxide. So this reaction is important to know this reaction. This is one reaction. One example is sufficient. Just do one example, that is this one, that is sufficient. So reactions with bases. The name of NaClO is sodium hypochlorite. So NaCl is sodium chloride, NaClO is sodium hypochlorite. Okay, now one important thing, that is what happens when a metal bonds with a non-metal. What happens when a metal bonds with a non-metal? Metal bonds with a non-metal. That is the next thing. So far we have understood the basic properties of metals and nonmetals. Now, what happens when a metal gets bonded to a non-metal? So let's do that now. So the next heading is what? Next heading is bonding. Bonding between a metal and a non-metal. Bonding between a metal and a non-metal. Okay. Bonding between a metal and a non-metal. Now, before that, you have to know that an atom may an atom may achieve stability. An atom may achieve stability by an atom may achieve stability acquiring acquiring the electronic configuration. An atom may achieve stability by acquiring the electronic configuration of an inert gas. It may do so. It may do so in either of the three ways. So if an atom wants to achieve stability, what will it do? It will acquire the electronic configuration of an inert gas. Now, inert gas has 8 electrons in the valence shell. Last time we discussed this in the previous lecture, that an inert gas has 8 valence electrons except for helium, which has 2 valence electrons. So other inert gases have 8 valence electrons in them. So if one atom wants to achieve the electronic configuration of an inert gas, it needs 8 electrons in its last shell, because an inert gas also has 8 electrons in its last shell. So in order to have 8 electrons in the last shell, what can it do? That's what we are trying to discuss. So it may do 3 things, any of the 3 things. So either the atom, either the atom may lose electrons, may lose one or more electrons. It may gain one or more electrons. It may share electrons. May share one or more electrons. These are the three different ways of achieving stability or acquiring the electronic configuration of an inert gas. Now, the bond formed, the bond formed between a metal and a non-metal bond formed between a metal and a non-metal is an ionic bond. The ionic bond is also called electrovalent bond. The bond formed between a metal and a non-metal is an ionic bond. Also, ionic bond is called an electrovalent bond. So, what is the characteristics of this bond? That we'll see. What are the characteristics of this ionic bond? So, in this process, a metal loses electron and a non-metal gains electrons. So, a complete transfer. So, a complete transfer of electrons takes place. A complete transfer of electrons takes place. The transfer is from the metal to the non-metal. The metal gives and the non-metal accepts. So the transfer of electrons is from the metal to the non-metal. So the transfer of electrons is from the metal to the non-metal. The bond formed due to transfer of electrons is an ionic bond and it is and it is a result of strong electrostatic forces of attraction. Strong electrostatic strong electrostatic forces of attraction. The attraction is between the cation and the anion. The attraction is between the cation and the anion. A cation is formed by a metal. So a cation is formed when the metal loses one or more electrons. A cation is formed when the metal loses one or more electrons. Thus, the cation is a positively charged ion. Thus, the cation is a positively charged ion. Why is it a positively charged ion? Because the metal has already lost electrons. If you lose electrons, you become positively charged because electrons are negatively charged. Since a metal has lost electrons, it will acquire a positive charge on itself. And a positively charged ion is called a cation. An anion is formed an anion is formed when the non-metal gains or accepts electrons. When the non-metal gains or accepts one or more electrons. Thus, the anion is a negatively charged ion. Thus, the anion is a negatively charged ion. So, the cation and anion both have come together, and the force of attraction holding the two is called the ionic bond. This force of attraction is called an electrostatic force of attraction, and because of this electrostatic force of attraction, the cation and anion together are held, and then that attraction is called an ionic bond or an electrovalent bond. Right? So an ionic bond is formed by, how is it formed? An ionic bond is formed when a metal loses electrons and when a non-metal gains electrons. So the transfer of electrons takes place from the metal to the non-metal. Because the transfer of electrons takes place from the metal to the non-metal, you get a bond, that is, there is a bond formed between the cation and anion. Anion is a negatively charged species, cation is a positively charged ion. So any compound containing any compound containing an ionic bond between two or between a metal and a non-metal is an ionic compound. Any compound containing an ionic bond between a metal and a non-metal is called an ionic compound. Some basic characteristics of ionic compounds. First, ionic compounds exist in solid state exist in solid state second, they conduct they conduct electricity in molten means when they have been heated and so the physical state is now liquid. They conduct electricity in molten and aqueous phase. In molten form and aqueous phase. So what is the meaning of this? That means when they are in a solid state, they will not conduct electricity. When they are in solid state, they will not conduct electricity. But when you put an ionic compound in water, then it splits into its corresponding ions, and that is why that solution now will become electrically conducting. Likewise, if an ionic compound is molten or fused due to the supply of heat, then also in the molten form it will conduct electricity. So remember, ionic compounds conduct electricity only when they are in molten phase and also when they are in aqueous phase. That means when they are in water. But ionic compounds do not conduct electricity in solid state. So you have to keep this in mind. Most of the ionic compounds are soluble in water, but not all. Most of them are soluble in water. That also you have to keep in mind. So these are the properties of ionic compounds. So we have completed the basic properties of metals and non-metals. Also, we have seen what type of bond is formed between a metal and a non-metal. Now we are left with different states of metal. That is, the metals exist in nature, and they exist in nature as what? That's what we are going to study in the next lecture. How are they obtained from the nature? They exist in one form, after that they are processed, and then they are obtained finally the form that we desire. So that conversion of the entire thing, so the processes that are involved in obtaining a metal from its natural repository or the natural source, all those things we are going to study in the next lecture.